What if he could get a shortcut to understanding, well, some of the biggest ideas in physics, like the fundamental forces that govern our entire universe?
Yeah, imagine diving deep into the mind of a Nobel laureate, hearing directly about his personal journey, the collective um, leaps of faith and genius that led to discoveries that really changed everything.
That's pretty much what we're doing today, isn't it?
Exactly. We're taking a deep dive into an extraordinary source, Nobel laureate Abdus Salam's 1979 Nobel lecture. It's all about the gauge unification of fundamental forces.
Oh,
Our mission here is to pull out the most important bits of knowledge, the key insights, to help you understand this epic quest to unify gravity, electromagnetism, the nuclear forces, and really see where science stood at that pivotal moment.
right. So we're going to explore, well, the history first. These cycles of scientific thought he mentions, which sound fascinating.
Definitely. And then we'll get into the personal story behind electroweak unification. It's quite a tale. And finally, we'll look at the cutting-edge stuff from back then, the late 70s. The big problems, the predictions, things like grand unification, and even preons.
Sounds great. Let's jump in. So, to kick things off, Salam starts by reflecting on Alfred Nobel himself, how his generosity way back fostered this prestige for science globally.
Yeah, he made some point about how significant this was, especially for the developing world. It sort of set a tone, didn't it, for international science?
It really did, but what I found really striking was how he uses history not just as background, but to show that science isn't this, straight line forward.
Exactly. He talks about these cycles and gives some amazing examples, like Michael the Scot.
Right. Tell us about him.
Well, 760 years before Salam's lecture, so we're talking 1217 AD, this young Scotsman travels to Spain, to the Arab universities in Toledo and Cordova.
Okay, way there.
His project, which was pretty audacious, was to introduce Aristotle to Latin Europe. But not from the original Greek, he didn't know it. He was translating from the Arabic versions being taught there.
Wow. So Europe was learning Aristotle from the Islamic world, essentially.
Directly. And it wasn't just him. He later went to Salerno, the medical school in Sicily, and met a Danish physician, Henrik Harpeskring.
Mm-hmm.
Henrik was writing about medicine, surgery, and he relied completely on Islamic medical texts. People like Al-Razi, Avicenna, and Michael was the one translating them for him.
That's incredible. It paints a picture of places like Toledo and Salerno as these real international hubs.
Absolutely. Scholars coming from the rich countries of the East, as Salam puts it, Syria, Egypt, Iran, Afghanistan, and also from the developing lands of the West and North, like Scotland and Scandinavia, a real melting pot.
But it wasn't always smooth sailing for these outsiders, right? You mentioned Michael faced some pushback.
Oh, yeah. Apparently, one of his masters told him to basically go back to clipping sheep and weaving woolen cloth.
Ouch. That kind of resistance. It feels familiar, even today, doesn't it? New ideas from unexpected places.
It really does. It speaks to that human element. And Salam connects this to a broader sweep using George Sarton's work, his history of science.
Sarton quantified these cycles.
Yeah, he divided scientific history into these half-century ages. And from 750 AD to 1100 AD, that's 350 years straight, Sarton identifies ages dominated by Islamic scholars.
Wow, 350 years.
People like Jabir, Khwarizmi, Razi, Masudi, Wafa, Biruni, Avicenna, Omar Khayyam, Arabs, Turks, Afghans, Persians, all part of this incredibly vibrant Islamic culture of the time.
And he mentioned other places too, didn't he? Like the Americas?
Right. The pre-Spanish Mayas and Aztecs.
Mm-hmm.
Incredible creativity there, too. Inventing zero independently, complex calendars, even pharmacological discoveries like quinine, in some ways ahead of their Western contemporaries.
But then there was a shift.
A profound one, yeah. After about 1350 AD, Salam notes, the developing world, as we call it now, started losing that scientific lead. Just occasional flashes after that, like Ulugh Beg in Samarkand or Maharaja Jai Singh in Jaipur much later.
So the cycle turned.
It did. And Salam ties it all together with his amazing quote from Al-Kindi from 1100 years ago.
What did it say?
Basically, it is fitting then for us not to be ashamed to acknowledge truth and to assimilate it from whatever source it comes to us. For him who scales the truth, there is nothing of higher value than truth itself. It never cheapens nor abases him.
That feels incredibly relevant for physics today, doesn't it? This global pursuit.
Absolutely. It's the perfect lead-in to the modern dream of unification. I mean, Maxwell had already done it a century before Salam, unifying electricity and magnetism.
Right, into electromagnetism.
And then Einstein, of course, had the grandest vision, unifying all the forces. That's the quest Salam himself took up.
So that sets the stage beautifully for Salam's own story, his personal journey towards unification. And it's interesting, he didn't start as a theorist, did he?
No, not at all. He actually started out in experimental physics at the Cavendish lab, working on tritium-deuterium scattering. But he admits he just didn't have the patience for it. He called it a sublime quality he sadly lacked. So, kind of reluctantly, he pivoted to quantum field theory.
Which turned out to be a pretty good move.
A very good move. He got deeply interested in renormalizability.
Okay, remind us what that is again, simply.
Basically, it's about making sure your theory doesn't break down mathematically, that it doesn't give you nonsensical infinite answers when you try to calculate things. You need it to make actual predictions.
Got it. And back then, that was a problem for some forces.
It was. Only theories with spin-zero particles seemed okay, renormalizable, which pointed to them mediating the strong nuclear force. But the weak force, the one behind radioactivity, seemed like it needed massive spin-one particles.
And that was a no-go for renormalizability.
At the time, yeah. It would look like a dead end. A non-renormalizable theory is basically unworkable. Big dilemma.
Okay, so then comes this pivotal moment for him, September 1956.
Right. He's at a conference listening to Professors Yang and Lee, and they're discussing this really radical idea. Maybe left-right symmetry is an absolute. Maybe it's violated in weak interactions.
Which was considered almost sacred before, right? Like a fundamental symmetry of nature.
Totally. And Salam's flying back to London on this uncomfortable military plane, can't sleep, just turning this idea over in his head. Why would nature do that?
And then something clicked.
Yeah. A question from his old PhD examiner, Rudolf Peierls, popped into his head. Years earlier, Peierls had asked him, the photon mass is zero because of Maxwell's gauge symmetry. Why is the neutrino mass zero?
Ah, and the answer came to him on the plane.
Pretty much. He realized the neutrino being massless pointed to another symmetry, chiral symmetry, this idea of handedness.
Handedness, like left-handed and right-handed screws?
Sort of, yeah.
Mm-hmm.
For a neutrino to be truly massless, it has to have a specific handedness, always spinning one way relative to its motion. And this meant nature had a choice.
What was the choice?
Either you have this aesthetically pleasing theory that violates left-right symmetry, the massless neutrino zooming at light speed, or you preserve left-right symmetry, but then the neutrino has to have a tiny bit of mass.
And he was convinced nature chose the first option? The symmetry-violating one?
He was certain. He was elated. But then,
Reality check.
big time, he rushes off to see Peierls, his old examiner, all excited, and Peierls basically says, nope, don't believe it, wouldn't touch it with a pair of tongs.
Oof. And Pauli, the father of the neutrino.
Pauli was even harsher initially, called the ideas pure nonsense.
Wow. Getting shot down by giants like Peierls and Pauli, that must have taken some guts to stick with his idea.
Absolutely. Huge intellectual courage.
Yeah.
Trusting your insight against the establishment. But then...
This experiment weighed in.
Exactly. Just a few months later, Wu, Litterman, Tellig, their experiments confirmed it. Left-right symmetry was violated in weak interactions.
Vindication.
Totally. Salam mentioned Pauli even sent him somewhat apologetic letters afterwards. Must have felt pretty good.
I bet. So these ideas about chiral symmetry then evolved.
They did. He extended it from just neutrinos to electrons and muons, and eventually proposed it as a universal principle for all fundamental particles, leading to the VA theory.
VA, vector minus axial vector. What does that mean in practice?
It describes the specific mathematical form of the weak interaction, confirming it only acts on particles with a certain handedness. And it cemented the idea that the weak force carriers had to be spin-one particles.
But that brings us back to the mass problem, right? How do you give these spin-one particles mass without wrecking the gauge symmetry and the renormalizability, the whole thing Pauli worried about?
Exactly. That was the huge roadblock for years. It seemed impossible. Like you build this beautiful theory, and then the crucial ingredient, mass, just blows it up.
Until
the Higgs mechanism.
Developed through the 60s by several people, Anderson, Higgs, Brouden, Engler, Grolnick, Hagen, Kibble. It was the missing piece.
And what did it do? How did it solve the problem? It provided this incredibly clever way for particles to acquire mass through their interaction with a background field, the Higgs field, while the underlying gauge symmetry of the equations remained intact. And crucially, Hooft later proved theories using this mechanism were renormalizable.
So it kept the maths consistent and allowed the force carriers, W and Z bosons, to be massive.
Precisely. It wasn't just a patch, it was fundamental. It allowed Salam and Steven Weinberg, building on work by Ward and Kibble too, to finalize the SU2 by U1
Now,
theory.
the electroweak theory, right, unifying weak interactions and electromagnetism.
That's the one, spontaneously broken SU2 of U1. Sidney Coleman had that great quote about it, turning the Weinberg-Salam frog into an enchanted prince.
Huh, I like that. And around the same time, there was this idea about a fourth quark.
Yeah, the Jim mechanism, Glashow, Iliopoulos, Maiani, they showed theoretically that you needed a fourth quark, the charm quark, to make everything consistent, to explain why certain reactions didn't happen when they otherwise should have. Another brilliant theoretical prediction before discovery.
Okay, so the theory was looking incredibly elegant, but theory needs proof. You mentioned Einstein's quote about needing experience.
Right, all knowledge of reality starts from experience and ends in it. And the big experimental confirmation came in 1973.
Gargamel at CERN.
Yep, the discovery of neutral currents.
Okay, what are neutral currents again? Why are they such a big deal?
So normally, weak interactions involve particles changing their electric charge, like a neutron turning into a proton. Neutral currents are weak interactions where particles interact without changing charge.
And the theory predicted these.
The electroweak theory absolutely predicted them. Finding them was massive confirmation. Salam tells this great story about being stopped in his car by one of the experimentalists, Musset, who just blurts out, "Are you Salam? We have found neutral currents."
Fantastic. A real eureka moment caught on the fly.
It really was. And then more confirmation came in 78 from SLAC and CERN. See interference effects between the Z boson and the photon.
So experiment really sealed the deal for the electroweak theory.
It absolutely did. Theory and experiment coming together beautifully.
Okay, so fast forward to 1979, the time of the lecture. The Standard Model is really taking shape. What did the particle zoo look like then?
Well, the picture was pretty clear, at least at the energies they could probe. You had three families, or generations, of quarks, each quark coming in three colors, red, yellow, blue, which is about their strong force charge, not actual color.
Right, governed by Sec3, the
Yeah.
symmetry of QCD.
Exactly. And then three families of leptons, electrons, muons, TASS, and their associated neutrinos. These were SU2 doublets paired up for the weak force.
But the third family wasn't complete yet.
Now, the top quark, the partner to the bottom quark, which had been found, was still just predicted. And this replication, these three near-identical families, that was already a puzzle.
Yeah, Salam asked that question. Does this imply something deeper? Like these 15 or 16 particles aren't fundamental, but built from something else.
Exactly. That question of elementarity is always there. Meanwhile, QCD quantum chromodynamics, the theory of the strong force, was looking good. There was indirect evidence for gluons, the force carriers.
But still big problems like confinement. Why we never see quarks or gluons on their own.
Yeah, confinement was, and still is, a major theoretical challenge. Why are they always locked up inside protons and neutrons? We understand it happens, but proving it rigorously from the theory is hard.
So electroweak theory, huge success. QCD, looking good but with puzzles. What about the loose ends in electroweak? The Higgs.
Ah, yes, the Higgs problem. Or problems, really.
Hmm.
Why the simplest Higgs? Is there just one? What's its mass? And it introduced a lot of arbitrary numbers into the theory, like 21 out of 26 parameters in the simplest version. That felt untidy.
Less like a fundamental explanation and more like fitting parameters. Could the Higgs be a composite?
That idea was definitely floating around. And other questions, too, like how perfect is the similarity between families? Are there more Z bosons waiting to be found? Minor tweaks? Maybe. But the really big idea was pushing beyond the Standard Model.
Grand unification, trying to unite the strong force with the electroweak.
Exactly, the electronuclear force. Ideas going back to 72, 74.
And what were the core concepts driving that?
Three main things.
Yeah.
One, putting quarks and leptons in the same family, the same mathematical structure, a multiplet of a larger unifying group. That was Petit and Salam. Big psychological step. Two, Georgi and Glashow went further, putting left-handed particles and their antiparticles all in the same multiplet. Very bold.
And three?
Three, using renormalization group ideas, basically tracking how force strengths change with energy to show that the different strengths we see could all derive from a single unified strength at some incredibly high energy. That was Georgi, Quinn, and Weinberg.
And that energy scale
Yeah.
was huge, right?
Astronomical. If you assume nothing new happens between everyday energies and the unification point, the scale M comes out around 1013 GeV or higher.
Wow, that's getting close to the Planck scale, where gravity dominates.
Right. And that enormous scale leads to the most dramatic prediction of grand unified theories, or GUTs.
Proton decay.
Proton decay. The idea that protons, the bedrock of matter, aren't perfectly stable but could decay, albeit incredibly slowly.
Why is that predicted?
Because if quarks and leptons are in the same family, unified by this larger symmetry, there must be new forces, new particles that can turn one into the other. A quark into an antilepton, for instance.
Leading to the proton falling apart.
Potentially. Different GUT models predicted different ways it could decay, and different lifetimes, anywhere from 1023 years to over 1030 years. Mind-bogglingly long times.
And experiments were being planned to look for this.
Oh, yes.
Yeah.
Huge underground detectors. It was seen as the crucial test. Salam noted that the early experimental limits were already pushing the simplest models, maybe requiring extra intermediate steps or particles to make the proton live long enough.
GUTs also made other predictions. Mass relations.
Yeah, relations between quark and lepton masses in different families. And fascinating connections to cosmology, potentially explaining why there's more matter than antimatter in the universe through processes in the very early, very hot universe where GUT physics would have reigned.
But even with all that elegance, there was still this issue of parameters, too many arbitrary numbers.
Really quite a few, yeah.
Yeah.
Even the simplest GUT model had something like 22 arbitrary parameters, better than the 26 of the standard model without unification, but still felt unwholesome, as Salam put it. Not quite the ultimate theory.
Which leads naturally to the next question. Are quarks and leptons really elementary?
The ultimate question, maybe. If they are, you've got maybe 45 fundamental fields, counting colors and spins and antiparticles. That seems like a lot.
But Salam brings up Einstein again, right? Einstein wasn't bothered by having 10 fields for gravity.
Exactly, because Einstein had a guiding principle, the equivalence principle. Salam quotes him. Nature was not economical of structures, only of principles of fundamental applicability. Maybe the simplicity isn't in the number of particles, but in the rules they follow.
Or maybe they aren't elementary after all.
Or maybe not. That leads to the idea of preons, or pre-quarks, that quarks and leptons are themselves composites of even more fundamental things.
Okay, what would these preons be like?
Simpler, maybe, each carrying just one type of fundamental charge. Paty, Salam, and Strafty had a model in 75 with 4 chromons carrying color and 4 flavons carrying flavor, within an SU8 symmetry group.
And there was this even more exotic idea involving magnetic charges.
Yeah, what if preons had magnetic charge? Magnetic forces are predicted to be much stronger than electric ones, so preons could bind incredibly tightly, forming quarks and leptons that appear magnetically neutral to us, hiding their structure until you hit immense energies. Very speculative, but intriguing.
Okay, so that's one direction compositeness. What about the other huge missing piece? Gravity.
Right, bringing gravity into the quantum unified picture. That's where things got really wild. Kaluza and Klein had shown way back that if you write Einstein's gravity in 5 dimensions...
The 5th dimension being tiny and curled up.
Potentially, yes. The amazing thing, the miracle, is that the 5D theory automatically spits out ordinary 4D gravity plus Maxwell's electromagnetism. The electromagnetic field just emerges from the extra geometry.
Wow. So maybe other forces could come from extra dimensions too.
That became a huge research program later, but even in 79, the idea was there. Maybe these dimensions curled up or compactified very early on, then came supergravity.
Supergravity, adding supersymmetry?
Exactly. Supersymmetry connects particles with different spins, matter particles, fermions, and force carriers, bosons. Supergravity extends this to include gravity, trying to unify matter, forces, and space-time geometry. It naturally lives in higher dimensions.
And there was another idea about topology, space-time being like cheese.
Huh. Yeah, Wheeler, Schoenberg, Hawking. The idea that fundamental properties like electric charge might be related to the very fine-grained structure, the topology of space-time itself, like tiny wormholes or handles.
So heading into the 80s, supergravity seemed like a promising route.
Especially extended supergravity. Just as Salam was giving his lecture, Kremer and Julia made a breakthrough, formulating a theory in 11 dimensions.
11 dimensions.
Yep. And the agreeable bonus, as Salam called it, was that this 11D theory, when reduced to 4D, automatically contained a large internal symmetry group, SU8, that wasn't explicitly put in.
SU8, but didn't you mention that for preons?
Exactly. That was the tantalizing connection. Could this SU8 from supergravity be the symmetry group of the 8 preons making up quarks and leptons?
Whoa.
And even more speculatively, could the force carriers of this SU8, the gauge bosons, actually be composite states within the supergravity theory itself?
Yep.
Made of simpler fields but acting like fundamental force carriers.
That's a mind-bending idea, gauge fields not being fundamental.
Deep stuff. Very speculative. But it showed the kind of radical thinking happening at the frontiers. Of course, the question becomes, How do you test any of this?
Right. What would be the experimental signature?
For supergravity, one key prediction was the gravitino, the supersymmetric partner of the graviton. It would likely be massive, getting mass via a super Higgs effect, and might show up in decays of particles like the Z boson. There was also Shirk's idea of anti-gravity effects from related particles. These were the kind of long-shot signals they were starting to think about. Hashtag outro.
What a journey. We've gone from, ancient scholars translating texts in Toledo all the way to the absolute cutting edge of theoretical physics in the late 1970s.
It really shows how this quest to unify nature's forces is this incredible human story, spanning centuries and cultures, full of personal struggles, brilliant collaborations, and these deep, persistent questions.
And it feels like the questions just keep getting bigger. As Salam pointed out, maybe the early universe itself becomes our main laboratory.
Absolutely. The energies involved in some of these unification ideas, or in probing preons or quantum gravity, they're likely beyond any accelerator we could build. So we look to the cosmos, to the aftermath of the Big Bang.
And we still don't know what we'll find. Will it be this grand plateau, as he put it, with maybe not much new until the Planck scale?
Or could there be whole new layers of reality just around the corner, maybe at 10 TV? New structures, maybe related to things like magnetic monopoles, we just don't know.
But the quest itself, the asking of these questions, that's what's amazing, isn't it?
That's the heart of it, that relentless curiosity.
Maybe we can end with that Oppenheimer quote, Salam included,
Yeah.
from 1953. It feels very fitting.
Yeah, it really does, Oppenheimer said. Physics will change even more if it is radical and unfamiliar. We think that the future will be only more radical and not less, only more strange and not more familiar, and that it will have its own new insights for the inquiring human spirit.
More radical, more strange. A perfect thought to end on.